Recording has started.
Today we are going to continue our discussions on the memory subsystem. So in the previous lecture 16, we talked about the overview of the memory subsystem, including the memory hierarchy. And we say we have different technologies to serve on different levels of the hierarchy. And the closest level to the processor is the cache. And we say that cache is implemented by the SRAM, static random access memory. So today we are going to talk about the details of the memory cell, the SRAM memory cell. So here this is a reference chapter from the Cedar Smith textbook and the recorded materials from last spring and Professor Asif Khan. So here's a history of the SRAM cache evolution over the past 30 years. So in the 1980s, we have the only one level of cache. So here you see L1 cache. But this cache is off chip, off the processor's chip. So basically you have two chips. One is the processor only for the logic, and then the memory. L1 cache is in a separate chip, and of course we have the main memory like the DRAM at that time. So this is the very early stage of the cache. So the trend is to embed the cache onto the same processor as the logic functions. So here you see later we embed L1 cache onto the processor's core, but still L2 cache is off chip. And later, L1 and L2 cache both are on chip. And nowadays, this is representative. So we typically have three levels of cache, and L1, L2, L3. All of them are on the same processor's chip. And the DRAM main memory is typically off chip. So here are the cache sizes for those three levels as an example. And in the last lecture, I showed the spec of my processors, and you can check that for your system as well. And the SRAM is one type of the random access memory, so it's a RAM. So what does RAM mean? It means that all the data in this memory can be read or write independently. So it's a random access. Random means that if you give an address, like the row address and the column address, then you can locate the memory cell, and then you can read or write the cell independent of other cells. So this is a key feature of the SRAM and also the DRAM. But later when we talk about the other memories like the flash memory used in your SSD, then that's different. That is not random access. In the flash memory, for example, today's NAND flash, when you write the data, you have to write the whole block. For example, if you want to write the data 0, then you have to erase the whole block first, and then you write the ones. So it's unlike the SRAM or DRAM. You can go to individual cell and read and write from there. But for the flash, when you write, you have to write the whole array or whole block. So that is different. And here, for the random access memory, we have shown this generic organization. This is also true even for the flash. We have the row decoder and the column decoder. So you have the row address and column address. So you can decode the address into the rows and columns. And we call the row as the word line, WL. And then we call the column as a bit line, BL. And the intersection here is the storage cell or the memory cell. So in today's lecture, we are going to discuss about this memory cell. That is the SRAM cell. So SRAM, static random access memory. So let's talk about the wording here. Static means no periodic refresh needed. This is with respect to the DRAM we are going to discuss later. In that case, periodic refresh is needed. Static, you can also think is like when the power supply is on, your data will be static. That means your data will be there as long as the power supply voltage is on. And this random access memory, as we just discussed, each cell or each bit in the array can be accessed. That means read or write independently. And another feature of the SRAM is that it's a volatile memory. Volatile means if the power supply is removed, then you will lose the data. But as long as the power supply is on, then the data is static. The data will be there. But once you power off the chip, then your data will be gone. So this is volatile. So any questions so far? So those are the key concepts for the SRAM. Okay. Then let's about the SRAMs in great details. So here, this is the SRAM cell, and we talked about earlier, SRAM is a binary memory cell. Binary memory means one cell is going to store only 1 bit information. So it's 1 bit per cell. And the actual implementation of the SRAM cell is shown here in this circuit schematic. You will see that it has a cross-coupled inverters in the middle. So here we see 2 inverters. And then we add 2 additional access transistors from the coupled inverter to the bit line. And the SRAM cell is a symmetric structure. So you will have bit line and bit line bar. And this is for the complementary access. So why is complementary? So the data you store in the SRAM cell will be only 2 options. Because this is 2 inverters in the loop, it will be a stable circuit. Why is that? For example, you can think if this is 0, like a ground, and then after the inverter, you get 1 VDD. And this 1 is input for the bottom inverter as well. Then the output will be 0. So this is a stable circuit. And also we call it a latch. So you can latch the memory state. This is unlike the ring oscillator we talked about earlier. So in the case of ring oscillator, we have odd number of inverters in the loop. Then the circuit is unstable, so the signals there will have the switching all the time. But this is the even number of inverters in the loop. In this case, 2 inverters. So it will be a stable circuit. You will only have these 2 options. One is if this left-hand side is 0, then the right-hand side is 1. Or if the left-hand side is 1, then the right-hand side will be 0. So you only have those 2 options. And actually, you only store 1 bit information because this is always complementary. So we typically will only look at one side of the circuit. And in this example, we assume the left-hand side is a BL, and we think the data is either 0 or 1. So this is the real data we want to look for. So the other side is complementary. So that means it's always opposite. So it does not store additional information. It's just a complementary pattern. And this is called the BL bar, the bitline bar side. So in our following discussions, we will always assume the data is referred to the BL side. Okay, this is the real data we are going to read and write. So this is the SRAM cell in the implementation, and actually you can draw this out into the transistor symbols, and if you do that, then this SRAM cell will become 6 transistor. So it's typically called 6T SRAM cell because it's 6 transistor in total. So what you have here is the inverter 1. You have those 2 red transistor, NMOS and PMOS for the inverter. And then the blue inverter 2, you have those 2 inverter here. And they are cross-coupled. So that means the input and output will be exchanged. So for example, here we define the N1 node. That is the output from the inverter 1. And then this will be the input for the inverter 2. So here you see that this N1 is output from the inverter 1, but this N1 is attached to the gate of the inverter 2. So this is a cross-couple. And then similarly for the N2, which is the output from inverter 2, that will be the input for the inverter 1. So here you see the N2 output of the inverter 2, and that is attached to the gate of the inverter 1, that is input to the inverter 1. And here we want to define a few concepts, a few definitions. So this N1 and N2 node are called the storage nodes because you store the data there, like 1 or 0. And as we discussed, we think the real data is in the N1. So that is what we want to look for, because N2 is always complementary. And then we have the BL and BL bar, bitline and bitline bar. Those are the columns. And then we have the word line, that is the row input. So the word line is controlling the gate of this pass gate transistor. So here we say this is a access transistor, and we call it pass gate, and it's PG. So here then we have this PG1 and PG2. So that's overall organization of this 6 transistor SRAM cell. Any questions? Okay, so out of those 6 transistors, you will see that you have 4 NMOS, right? So here the PD pull down is NMOS, and then this PG pass gate is NMOS, and then the pull up PMOS. And on the left hand side we call it PD1, PG1, PU1. On the right hand side we call PD2, PG2, and PU2. And next, we are going to discuss the operations for the SRAM cell. So there are 3 operations, or let's say 3 modes. The first mode is the hold operation. Hold operation means you want to keep the data in the SRAM cell. So if you keep the data, you don't want to read or write, you just want to keep. Then here, sorry, go back. So this is a keep the data. If you want to keep the data, then what you want to do is to turn off the word line. WL is 0. 0 means ground. So here in today's lecture, when we talk about 0, that means we are going to ground. When we talk about 1, that means we are going to apply the power supply VDD. So here the word line is 0. So the PG1 and PG2, those two pass gate transistor, because they are NMOS, so the gate is 0. Then the VGS will be 0 or even negative. So then this is like the cutoff for the PG1 and PG2. So if those two transistors are off, then to the first order there's no leakage current through the pass gate transistor if we ignore the subthreshold currents. Then they are like open circuit. So basically the memory cell in the middle, that's a latch, is isolated from the outside, which is a BL and BL bar. Because of the BL and BL bar is going to connect to the end of the array, and then there's a interface circuit to communicate with the outside. So then if you turn off the WL, it's like the memory state is latched in the middle, and it has nothing to do with the outside. So then this is a hold operation. So here, as we discussed, you only have two possible options. Either the N1 stores 0, N2 stores 1, or N1 stores 1, N2 stores 0. So this is a stable circuit. This is how you store the data on the SRAM cell. And if you think about the computer program you are coding, right, the temporal data saved in the cache are actually stored as the voltage 0 and the voltage VDD into those circuits. So this is a hold operation. Any question? And then let's look at the read operation. So you want to read the data out from the memory cell to the outside of the array. For example, read the data from here and then send the data to the logic unit to do the computation. Then we want to read out the data. So there are few steps. First one, we need to pre-charge the VDD. Pre-charge the bitline and bitline bar to be VDD. So here bitline and bitline bar pre-charge to VDD. Pre-charge means we are going to bias the BL and BL bar to be VDD. And then after that, you disconnect whatever you bias circuit to the bitline and bitline bar. So the bitline and bitline bar will be floating. Why it can float? Because there will be parasitic capacitance to the BL and BL bar. So the parasitic capacitance for the CB or CBL, CB and CBL and CBL bar. This is because this is like a non-wire, right? So the BL is a non-wire, and we talked about earlier in the interconnect. So you have wires, and between wires you have dielectric or insulator. So you have like a parasitic capacitance between wires. Then this is a non-wire. Then suppose you should have a reasonable capacitance here attached to the bitline. So this is pre-charge this bitline, essentially pre-charge the bitline cap to be VDD. So this is the first step before you read the data. And the second step is to turn on the WL. So you are going to turn on the WL. So now the WL will become 1, and then this is VDD. Then we are going to analyze the circuit according to the bias condition. First of all, this is turned on to the VDD. So here PG1's gate is VDD. And then the BL is pre-charged to VDD. So in this example, we assume N1 stores 0, N2 stores 1. So if N1 is 0, you see the PG1, this transistor, is turned on, and actually it's in the saturation, right? Because here NMOS, VGS is here, and VDS is here. So this is the saturation condition for the PG1. So you have current flow, the drain current, like this. And then if you look at the PD1, it's also on, because the PD1's gate is attached to this N2 node, and N2 you store 1, so that means this gate is VDD. So PD is NMOS, so VGS larger than the threshold, and the VDS, although it's small, this is kind of close to 0, but this is on. It's more like in the linear region when the VDS is very small. So this is like linear region for the PD1 and the saturation region for the PG1. Then you will have the current flow from the bit line to the ground. So you see green path. So this is a current flow. This current is going to discharge this bit line cap. Initially, here you have the VDD, but you have this current flow. So this current is going to extract the charge out from the top plate of this cap. Then this voltage is going to decay. That means the voltage will become VDD minus delta V. This is the change of the voltage. This is on the left-hand side. We can also look at what happened to the right-hand side, to the BL bar. And actually nothing will happen. Why? Here the PG2 is VDD, the gate. And then the BL bar is also projected to VDD. And N2 node, because it stores 1, so it's VDD. So you will see that the PG2 source and drain the same potential. There's no current flow. No current, that means here no change. So the BL bar voltage will remain at VDD. Now you see a difference between the BL and BL bar in terms of voltage. So BL will have smaller voltage, VDD minus delta V, and BL bar will be kept at VDD. Then this will be read out as the data you stored by the peripheral circuits. So after that, there's peripheral circuits called sense amplifier. So at the end of the column, it will be attached to the sense amplifier, SA. So this SA is going to detect the small difference and amplify it. So the BL will be VDD minus delta V, BL bar will be VDD. Then this is like smaller. Then the output, this side will be 0, this side will be digital 1. And so the sense amplifier is going to amplify the small signal. If the left-hand side is smaller than the right-hand side, then the left-hand side will be output as digital 0, and the right-hand side will be output as digital 1. Or if you have the opposite relationship, then the left-hand side will be 1 and the other side will be 0. So this is the sense amplifier, the job of the sense amplifier. Essentially, we are going to read out the data from the memory cell, relying on the small difference that you develop on the BL and BL bar. If you look at the waveform or the timing diagram here, initially we precharge both BL and BL bar to be VDD, and then we turn on the WL here at this moment. We turn on the WL from 0 to 1. Now the BL is going to decay due to this current. So the BL voltage will decrease, but BL bar will remain the same. So over some short period of time, then we're going to have this difference between the BL and BL bar by this delta V, and then this sense amplifier will detect this small difference and amplify the small difference to be digital 0 and digital 1. So this is how we read out the data. Any questions? This process is a little bit complicated, and you can read the comments I have input here for the description of this process. But if you label the voltage on all the terminals here, then you can determine the operation region for those transistors, and then you can look at how the current flows. Then you should be able to analyze how the voltage will change in this circuit. And then let's look at one requirement on the read operation. That is the N1 voltage here. So here we are drawing only this part, because in this process only the PG1 and PD1 are active, so current are flowing here. So let's only look at this part. So if we only look at this part, then we are going to have this two transistor like this, and then you have the beta capacitance attached to the beta. So you can approximate the transistor using the resistor, as we discussed before, as a rough estimation. So this is your BL, and then here is the N1 node. This is the cascade, and this is the pull down. So if you think those are transistors, those are resistors for those two transistors, then here there's a requirement on the N1 voltage. So during this process, initially N1 is 0 voltage. This is what you store, the data 0. But during this read operation, so the N1 voltage will increase a little bit. Why? Because this is a voltage divider. If you have current flow, then this N1 voltage must be higher than ground, because this is a voltage divider. So then this N1 voltage will be higher than the ground. But you don't want this N1 voltage to increase too much. So in this process, N1 is going to change from 0 to some voltage, let's say delta V. But you don't want delta V to be too large, because after the read operation, you want the N1 goes back to 0 again. Because the read, you are going to read only. You are not going to change the data after the read. So you only want to detect the data, but you don't want to flip the data during the read. That means if you think this is like a noise or disturb to the N1 voltage, you want this disturb or this noise to be small as possible. Then after the read operation, then if it's within the noise margin, because we have the inverter, right? Two inverters. So if this disturb or this noise is within this noise margin, it can go back to the original state. Therefore, you don't want this delta V to be small. You want the delta V to be small. This is the increase of the N1 voltage. You want this one to be small during the read. In other words, here you have this voltage divider. You can think the resistance of the pull down, compare that to the resistance N1 voltage, this delta V to be small. You can identify the relationship, relatively speaking, which resistance is smaller. This is the voltage divider. If you want to have N1 close to 0, then this resistance PU should be small, right? Then the N1 will be close to 0. So you have this condition. Or in other words, we want the PU to be stronger than Pg. Stronger in terms of the conductance, right? The resistance, and then stronger is the conductance. Then you can translate that into the W/L ratio, because you know the resistance is the equivalent resistance is inversely proportional to the W/L, and then the W/L of the PD will be larger than the W/L of the Pg. So this is a requirement we need to satisfy in this rate operation. So when you design the circuit, you have to make sure the transistor size for the pull-down transistor larger than that of the cascade. And on the right-hand side, we show the timing diagram of this rate operation. So as we discussed, before you read, you should pre-charge both bit line and bar to be VDD here. And then we turn on the wire line from 0 to 1. And then due to the current, this current, then the BL is going to decay, and BL bar will maintain. So we have this delta V. We have this delta V. That is a small difference we want to sense by the peripheral circuits, in particular by this sense amplifier. And during this process, the N1 node is going to increase the voltage. And we want this increase of the voltage to be small, delta V, to be small. Because after the read operation, then we want this to come back, because you store 0 at N1. After read, you still want to store 0. So then this should be minimal increase. To make sure this is a minimal increase, then we have to satisfy this condition. So we can define the ratio W/L of the PD divided by the W/L of the Pg. So this is larger than 1. So we say that this beta ratio needs to be larger than 1. So any questions? Can you explain why there is a difference in the voltages? So once again, you see here the BL, you have this current, right? So this current is going to discharge this capacitance that is attached to the bit line. So it's like this current is going to extract the charge from the bit line. Therefore, the voltage will decay, because the voltage is related to how many charge on this capacitor. So then the bit line will decay with this voltage will decay with this current. But as on the bit line bar side, there's no current, so no change. Therefore, you can have the difference delta V between the BL and BL bar. Any other questions? And then here the key point is that we need to make sure the pull-down transistor to be stronger than the pass gate. In other words, the W/L of the pull-down needs to be larger than the W/L of the pass gate. And then we can also think about the speed of the read. So for any delay in the circuit, as we discussed before, the delay is due to you discharge something. So for example, if you get the delta Q, the charge out from the bit line cap by this current of this pass gate, then the time is the charge divided by the current, and the delta Q is essentially the bit line cap times the delta V, the voltage change on the cap, and then divided by the current. current. So typically the baseline capacitance is, there's a typo here, so it should be 10 femto to 100 femtofarad. And the delta V you need to sense the difference is typically 100 millivolts. So if the current is like a microamp, then you can get the readouts within like a nanosecond. So we can do that here. For example, if you take the lower end, like 10 femtofarad, 10 femto, times the voltage difference, 100 millivolts, that is 0.1 volts. And then divided by the current. If the current through the transistor cascade is 1 microamp, then you see here 10 femto times 0.1 is 1 femto. 1 femto is 10 to minus 15. And then here 1 micro. 1 micro is 10 to minus 6. So you get 10 to minus 9. And that is 1 nanosecond. So you can get the readout within nanosecond. A nanosecond, if you translate that to the clock frequency, is like 1 gigahertz. So if you want to further reduce the delay or increase your clock frequency, then you can increase the size of the transistor, because those current, is proportional to the W over L. In the current equation, you have the W over L. So if you increase the size of this transistor, then you will increase the speed. Any questions?